I am Mauricio. My teammate is Miles. We will present the paper Skip Connections Matter on the transferability of adversarial example generated with resnet. We follow the topics, a brief introduction, background and related works. We talk about the skip gradient method, SGM, show how it works. And then Miles will present the case study with the experiment and results. We conclude and open to discussion. Uh, so let's start with the introduction, why this matters. Uh, we know state-of-the-art deep neural networks employ skip connection. Examples of such models are resnet and densenet. And here we see a skip connection. Let me turn on the pointer. Uh, this is a convolutional block. It's called a residual block, and this is the skip connection. It connects the input of the convolutional block directly to its output, and the backpropagation occurs both ways. It occurs through the skip connection and also through the residual block. It helps to preserve low-level filters and prevent performance degradation when we add multiple layers to the architecture. And authors ask the question, what if you set a preference to skip connection gradients over residual modulus gradients? And they investigate that. Also, we know the trade-off of white box and black box setting. White box fools better, but it did not transfer as good to other models, while the black box setting does not have a good transfer, a good success rate fooling the model, but it transfer better to other models. Previous work, authors say that previous works treat the entire network as a single component, and they do different. They investigate elements of the network architecture, in particular, skip connections. So here is one of the experiments they did. We see here the three last residual blocks of ResNet 18 architecture. These numbers are the success rate for the attacks. This first one is in the white box, and the second one is in the black box, which they tested against the target model VGG19. The green path here is when they used the skip connections gradient. And this way here, when you go left, it's when they used only the residual modulus output gradients. So we see clear here that for the black box setting, we have better success on the attacks for when considering the skip connections. And here we see also for the white box setting, we have a better fooling rate for when consider only the skip connections gradients. So going on, the question of whether or not a deep neural network architecture itself can expose more security weakness to adversarial attacks is an unexplored problem. And they do explore this question. So the paper enlists three contributions. The first one is what we could call a vulnerability, that the skip connections allow easier prediction of high transferable adversarial examples. And they propose a method to exploit that vulnerability, the SGM method that crafts adversarial examples using skip connections, gradients. And also they enlist as contributions the experimentation they did to show that the methods boost performance, boost attacks against boost existing attacks and provides more transferability. So now let's talk about related works, how this SGM will be compared to. And they enlist as white box attacks. The Fgsm, we know very well, fast gradient sign method. We do a step, the size epsilon step, a single step epsilon toward in the direction of the gradient. And also well known of us is the PGD, project gradient descent. It gives a step size alpha in the direction of the sign of the gradient, update the current iteration, and project it into the epsilon ball. As black box attacks, they for black box now we keep in mind they have a source model. They are crafting adversarial example in source models that has a skip connection, and they are targeting attacks to several different models. So they use the momentum iterative boosting to compare. This is we have already seen this as well. It incorporates momentum to the gradient computation, and the diverse input. We saw this in the same paper. The diverse input do translations. If you recall, they do upscales, random upscales, and random cropping with probability p, and they do this for computing the gradient sign and to update the interaction. And they also compare with the translation invariant method. This is new for us. This uses a matrix W. This matrix has dimensions 2k plus 1 by 2k plus 1, where k is the maximum number of pixels allowed to shift. And this W works as a convolutional kernel here. And the notion behind this is as if you had 2k plus 1 squared translations of the image of the input, and then you do a weighted sum of its gradients. And the author said it was originally proposed against secured models, and it will be present next week. So we'll get more familiar with that then. So let's go into the skip gradient method itself. What is SGM? Do you remember ResNet? There's a lot of models that use skip connections. And here we see illustration of the three last residual models of a given architecture. And we have here the output. Z3 is ZQ plus F3 of ZQ, and so on. ZQ is Z1 plus F2 of Z1, and so on and so forth. And if you get this, we can replace in this equation, and to compute the derivative of the output with respect of the input. Sorry, to get the derivative of the loss function with respect of the input, we do this formula, and we apply the chain rule and simplify. We got something like this for three residual models. Then we can extend this to L residual blocks, and it's something like this: the product of these two components. And we see here this part is corresponding to the residual model output, and this part is corresponds to the skip connection. What do? They include a decay factor gamma. The decay factor gamma is here to reduce the impact of the residual model. So keep setting a preference in the skip connection part of the gradient. And then we have the formula for the skip gradient method. It's this. We see here it's pretty much look like the PGD. The only difference is we set the preference on the skip connection over the residual output model. This method can be used combined with existing methods. and it does not add any computational overhead. Since we just add a decay here, it has the same complexity as the method itself. And for multiple step, they when they say only SGM for the multiple step, they are doing using PGD as base, and when they use single step, it is like the Fgsm. So a summary of SGM, it's a multiple step on-target black box attack, and it exploits skip connections. It does not require any computational overhead, and it can combine it with existing attacks to boost its performance. And now I will let Miles introduce the case study.
So yes, like I was saying, we're going to go over a quick case study, and then we're going to go over extensive results that the authors produced for this study. The first thing I'm going to do is I'm going to go over the overview of the experimental setup. The authors chose 8 different source models, first 2 being regular residual block-based networks, the ResNet 18 and ResNet 34. ResNet 18 came with 8 skip connections. ResNet 34 came with 16 skip connections, so there's double the surface there for them to exploit. The ResNet with bottleneck residual blocks, I'm sorry, ResNet 50, 101, and 152. The bottleneck residual block basically means that there's a 1-by-1 convolution immediately before and immediately after the residual blocks, so it kind of just squeezes in there, and then they do the skip connection around that. They also included 3 different variations of the dense net, the 121, 169, and 201 blocks. These are really interesting because they do increase the density of skip connection within the model. So for each output of each residual block, they're connected to all the successive dense net or residual blocks afterwards. For the target models, they chose these unsecured models, the VGG19, ResNet 152, and ResNet or DenseNet 201. They called these equivalent of a white box attack, but it was done in a black box setting. They also chose the squeeze and excitation 154 model, Inception V3, Inception V4, and Inception ResNet V2. The SE154 through the Inception ResNet V2 are state-of-the-art classifiers that are well beyond the scope of this paper. So we won't really get too into their architecture at all. For the secured side of things, they decided to use adversarial trained ensembles based on an ensemble of 3 Inception V3 networks. The same thing, just with 4 for the Inception V3 ensemble 4. Inception ResNet V2 was also put together with ensemble of 3 different adversarially trained networks. So basically for each of the comparisons, they chose 5,000 random images from the ImageNet validation data set that were already prior classified correctly by all the source models. And for that, they performed black box attacks on them. For all the attacks, they used the L infinity with a perturbation of epsilon equal to 16. Unless I specify otherwise later on with the later results, we can assume that epsilon was 16. The decay factor by default was 0.5, unless, as stated, it would be a different value. For the case study, they did a 10-step iterative attack, and they ran 5 runs of an untargeted attack against a particular model that we'll get into next. So between the 5 different runs, they would take the average of all 5, and that would be your fooling rate for the result. So for the first result that they did for their case study, they compared just a plain SGM attack against a projected gradient vanilla attack. What you see here is the source models in the header of this table, and then all of these were targeting an Inception V3 attack. As you can see, projected gradient descent kind of had very low fooling rate throughout. However, when you apply the skip gradient method to the ResNet, there was just kind of a small boost there, but when you include more skip connections, you really see a stronger boost. Kind of working through the bottleneck ResNets, there was more of a modest increase, but the real killer here is when you get into the dense nets where there's a lot more skip connections to work with, the boost to the fooling rate is just much, much stronger. Moving right along, they baselined some other parameters for the remaining comparisons. So what we'll be comparing against is FGSM for single step attacks, and for projected gradient descent would be in an iterative setting. Same for the momentum iterative boosting, diverse input, and translation invariant. So for a target model, if it was a secured model, they chose to use a 10-step attack. If it was a secured model, they used a 20-step attack. For the iterative attacks, they set the alpha factor to 2, so step size was 2. And when they were attacking a resnet, by default, the gamma value was set to 0.2. And for dense nets, it was 0.5. When they did a single step attack for FGSM, you'd simply add 0.3 to 0.2. So you would have 0.5 and 0.7 respectively for the single step attacks. From this point forward, when I say something to the effect of SGM, referring in the one step, we're really talking about FGSM plus SGM. And likewise for projected gradient descent, that would be for the iterative case. For the models where we're using VGG, ResNet, or DenseNet as the targets, the images were cropped down to 224 by 224, or for the inception-based models, they were 299 by 299 otherwise. They also went ahead and baselined the threat model. So basically, we're simply stating that adversarial examples are generated on a source model. They're used to attack a target model. Kind of goes without say. As I said before, the testing hyperparameters are the same as the projected gradient descent parameters, unless stated otherwise for a specific purpose. The first thing that they examined was the one-step transferability against secured models. And what you see here is on the left, the 2 best source models for crafting this attack. They generated adversarial examples on these source and applied it to these models as the attack. In this case, you can see that translation invariant did outperform SGM in a couple cases, and SGM was a little bit better for the ResNet and the DenseNet, and presumably SC154, where there may have been a few more skip connections, as well as the ResNet v2. Where the source model had way more skip connections to work with, SGM did perform astoundingly better. And what this tells us is that it does not transfer as well to a different base architecture if there are not enough skip connections in the source model. Crafting adversarial examples without those skip connections leads to a less transferable attack. And basically restating the same, yeah, it's more effective when you have more skip connections to work with. The net multi-step transferability, this basically the same. Our 2 source models are 152 and 201. So let's get it right out of the way. The white box equivalences, pretty much the same, really high 99%. But when skip gradient method is given time to do its job, it does a really effective job of fooling the target network. As you can see, it wins out against all other methods here with the multi-step. It does show a modest improvement against the inception-based networks, and it basically, we're highlighting again with the dense net, you're getting a strong increase when you have more skip connections to work with in your source model, as evidenced here on the bottom row. So when we're attacking a VGG network here, the kind of interesting thing here is that the deep source models do not perform as well against a shallow model as they do when you target a deeper model. Like when you're attacking SE154 or V3, PG or SGM does actually end up doing way better than it would overall in the end run with VGG 19. However, the overall success rate for every model is lower. SGM does show a better improvement with the deeper models. They also examine combining attacks with SGM. So here we see they targeted the DenseNet 201 model with momentum iterative boosting. And when they combine it with the SGM method, you end up with very significant increases, as much as almost 22%. Same thing for diverse inputs. You get close to 21% increase on the SE154. And when you combine momentum iterative boosting with the diverse inputs, there's more to be gained by applying the SGM model to that. They also examined the transferability against robustly trained models. SDF does not translate very well by itself as a vanilla attack against robustly trained models. That kind of lends itself to TI, which we'll see next week. That's actually designed to attack a robust model. And the thing to take away from this slide really is that SGM can be combined with other attacks and you still get very good results by combining it, and more so when you combine it with more skip connections. So to take a little bit closer look as the SGM attacks are concerned, they evaluated variations in gamma. And what they found was when you're attacking dense nets, gamma kind of peaked out at 0.5. If you look here, the dense net attack is the dashed lines, and the gamma value is decreasing. And what that means is as you make a smaller gamma parameter, you are squashing the residual weights from the network a lot stronger. However, once you get to 0.5, you start losing that high level class data from the residual blocks. So the fooling rate starts to fall off here for the dense nets. Similarly for the resnets, it does require a bit stronger of a gamma factor to start crushing out the residual weights. So it peaks at about 0.2. And as we recall, these were the default values that they set earlier on in the study. Extending out to squeeze and excitation 154 and inception V3, you pretty much see more of the same. We still have that same peak at 0.5 and 0.2 respectively for the resnets. And what this shows us is that the gamma is more dependent on the source model itself than it is for the target model. They also crafted adversarial examples on ensembles and attacked both unsecured and secured models. Here they used a source model of ResNet 34, 152, and DenseNet 201 to craft an attack against these target models. Interestingly, the inclusion of 152 and 201 in the source kind of maxed these out, and there was really nothing to be gained there. SGM in the case of VGG and SE, as well as Inception V3, it won the battle there. But when you got to Inception V4 and the Inception ResNet, the diverse inputs just barely beat SGM. But again, SGM being the runner-up here, combine those two and you end up with improved results. You get more of the same when you look at the secured models and attacking the ensembles of inceptions. TI, as before, was the winner overall, but when combined with SGM, we ended up with a stronger attack. They also finally looked at weak whitebacks attacks. These would be Singlestep Fgsm attacks. So here, looking at the source and target models being exactly the same. And when we apply the SGM method to basic FGSM, in each of the cases, we end up with a slightly better attack against the maximum perturbation being set to epsilon 8. And they also examined the variation of epsilon across resnets and the dense nets. Again, you see kind of the same pattern going on here. So anything below an epsilon of 2, there's simply just not enough loss there to really get any good usefulness out of it. And between 4 and 16, you notice that there's a trend going downwards on both the dense nets and the resnets, but the attack strength overall. So when you look at the lines here, your solid lines are the vanilla FGSM, and then your dash lines would be the FGSM with the skip gradient method combined. You always end up with the skip gradient method doing better. And the reason that the attack strength does improve is because it is allowed to use the loss better. However, the overall accuracy becomes lower simply because of the complex loss space. And then once you get above 32 and 64, there's just so much perturbation there, everybody's going to get way better. So I'm going to go ahead and wrap up here. And basically what we found here from the results is that skip connections are very useful when using the SGM to compute adversarial examples. They're very transferable, again, from network to network, especially when there's a lot of skip connections available. The extensive results in this study show that SGM not only improves existing attacks, it's even there to improve very marginally on very weak attacks. It also provides us a reminder to be mindful when we introduce new capabilities to fresh new architectures that we could be introducing new vulnerabilities into our work. So I was personally for this article, this paper, just simply because FGM is a very simple concept. It's easy to wrap your head around. It's very efficient. It doesn't add a lot of computational overhead. It's flexible enough to boost other existing gradient attacks. The authors did test extensively from model to model, combinations of models, both against unsecured and secured models, and they showed some very good results therein. For the stated purpose of this paper, it does show transferability, and it's also with respect to the skip connection, so it kind of validates the claim that skip connections are there to boost the transferability of black box attacks. And yeah, like I said, restating, it does show improvement in all transfer attacks. And I'll let Mauricio go ahead and fight against this paper.
So as weakness, we can you go for? So the fooling rate boosts only when you have enough depth in the model. It's one weakness. You need a deeper model to do it. Then Snap provide more skip connection, but when they use resnet was more effective to craft the adversary example that who secured models, and they could not explain why, or they only commented that. Also, SGM alone is not sufficient to attack secured model. It has to be combined with other methods to be efficient. And the model, the SGM attack is not as good for white box setup. It's good for the black box setting. We saw some small discrepancies on the results we see in the text and the values shown in the tables, maybe because they are reporting a specific run and not the average. And it was only tested in ImagineNet. They could have tested in other data sets.